In this module, we are going to turn to a slightly different aspect of Poisson process. So we start with the definition of Poisson process that we started with, but ask a very different question. It's a question about, you can call it infinitesimal behavior. Roughly speaking, take a very small time interval. By that I mean the time interval is of a very small length, and then ask, what is the probability of having one arrival in that small interval, no arrivals in that small interval, or two or more arrivals in that small interval? So we are going to show that, of course, it's clear that as the length of the interval gets smaller and smaller and smaller, the number of arrivals, probability of the number of there being no arrivals gets closer and closer to 1, and the probability of there being one arrival in a small time interval, or 2 or 3, all these things go to 0. However, there is a quantitative difference between the probability of there being one arrival in a small time interval and 2 or more arrivals in a small time interval as the length of time interval goes to 0. So what this distinction is going to be very, very important. What we are going to show is, of course, both of them go to 0 as the length of the time interval goes to 0. However, the probability of there being exactly one arrival in a small time interval goes to 0, but it goes to 0 at the rate at which the length of the time interval goes to 0. In other words, we will show that the probability of one arrival in a small interval is going to be approximately proportional to the length of the interval plus an error which goes to 0 at a rate faster than the length of the time interval. Whereas, if we consider the probability of 2 or more arrivals in a small time interval, that goes to 0, and not only does it go to 0, it goes to 0 at a rate faster than the length of the time interval. So there is a quantitative difference between the probability of there being one arrival in a small interval and 2 or more arrivals in a small interval. Of course, 1 minus all this would be the probability of no arrivals in a small interval. So this is something that we are going to exhibit, but we are not going to stop there. Then what we are going to show is that this property, apart from the property of starting from 0 and having independent increments, this additional property, namely how the probabilities of there being different kinds of arrivals, no arrivals, one arrival, 2 or more arrivals in a small time interval, how that behaves also characterizes Poisson process, in the sense that if we take a counting process starting from 0, having independent increments, but no assumptions on the Poisson distribution, only assumption is that on small time intervals, the probabilities of there being 0 arrivals or 1 arrivals or 2 or more arrivals behave in this particular fashion would characterize a Poisson process, and thereby leading to a third definition of Poisson process. So what we are going to do in this module is for the Poisson process with rate lambda, we are going to get a third characterization. So we start with another interesting property of Poisson process with rate lambda, which will, as I said, eventually lead to a third definition of a PP lambda. So what it involves is examining what can be called, it will be clear as we go along, but it can be called roughly the infinitesimal behavior of PP lambda. That is, the dynamics of the process, Poisson process, over infinitesimally small time intervals. Alright, so let's try and understand what that means. So let NT as usual be a Poisson process with rate or intensity lambda. Now fix a small time interval t to t plus h. Of course, that means that h is small, so the length of the interval is very small. So what I'm going to ask is, how many events can occur in this small time interval? From definition, we know that the number of events or arrivals during this interval t to t plus h is given by nt plus h minus nt, and that is a Poisson random variable with parameter lambda h. So that we know that it can take the value, any value k, with probability e to the power minus lambda h to the power k over k factorial for all k. So theoretically there is a positive probability of there being any number of arrivals in this short time intervals. But the important thing is that these probabilities are going to be very, very small for k bigger than or equal to 2. So let's see. So in particular, if I look at the probability of there being no events in this interval, that is probability that nt plus h minus nt is 0, that probability is e to the minus lambda h. The probability of there being exactly one arrival, that probability is lambda h into e to the minus lambda h. And if I club together and look at the probability that nt plus h minus nt is greater than or equal to 2, that is 2 or more arrivals in this small time interval, that probability would be of course 1 minus the first two probabilities, because that's a complement of there being 0 or 1 arrivals. Okay, now from these expressions it should be clear. See, our aim is to look at small h. So in principle we would like to ask what happens to these quantities as h gets very, very small. So theoretically what happens to these as h goes to 0 plus. So from these expressions it's clear that as h goes to 0 plus, that is h decreases to 0, the first probability e to the minus lambda h we all know goes to 1, whereas the other two probabilities clearly go to 0. Lambda h into e to the minus lambda h goes to 0 because e to the minus lambda h goes to 1, and then the factor lambda h would make this whole thing go to 0. And then as far as the third expression is concerned, you can see that 1 minus e to the minus lambda h goes to 0, lambda h e to the minus lambda h goes to 0, so this last probability also goes to 0. But that's only not fine enough. So what we want to make is a slightly finer statement which will capture the rates at which these convergences take place. So the first probability going to 1, the second and third probability is going to 0. At what rate do these quantities go to 1 or 0 respectively as h goes to 0 plus? So there we use this well-known fact that e to the power minus lambda h minus 1 over h goes to minus lambda as h goes to 0 plus. So from this, using this, you can easily deduce that the probability that nt plus h minus nt equals 0, that minus 1 minus lambda h divided by h goes to 0, because the probability is e to the power minus lambda h, and e to the power minus lambda h minus 1 by h goes to minus lambda, and then you have minus and minus plus lambda h over h, of course that's equal to lambda, so therefore this goes to 0. Similarly you can check the other two things. So in all three what we have obtained is something divided by h goes to 0 in all these cases. Now we want to express these statements in a more conventional way. We recall a standard notation from calculus. So here's a notation. One writes for a function f, one writes that fh is little o of h as h goes to 0 plus, simply to mean that the limit as h goes to 0 plus of fh over h goes to 0 is 0. So roughly what it means is that fh goes to 0, but fh goes to 0 at a rate faster than h, so that even if you divide fh by h, it still goes to 0 as h goes to 0 plus. Okay, so this fh is little o of h as h goes to 0 plus, simply one way of thinking about it is that fh goes to 0 and it goes to 0 at a rate faster than h. It's easy to see from the definition that if you have, let's say, k many functions, f1, f2, fk, such that all of them are little o of h as h goes to 0 plus, in the sense that if for f1 h by h, f2 h by h, fk h by h, all of these goes to 0, and suppose a1, a2, ak are some real constants, then this combination of fjh, aj, fjh summed over j equal to 1 to k, that also is little o of h, and that's a simple consequence of the definition. Okay, so just keep this two first notation and this little simple fact in mind. Then these observations about the probabilities that we've seen above, they can be expressed in a somewhat neater way in the following. So using these notations, our observation on the Poisson process lambda can now be expressed in the following sense. If nt is a Poisson process with parameter lambda or rate lambda, then for any t greater than or equal to 0, the probability that nt plus h minus nt equals 0, that is 1 minus lambda h plus little o of h. Remember, what that simply means that this probability minus 1 minus lambda h is little o of h. In other words, that probability minus 1 minus lambda h over h goes to 0, and that's exactly what we have observed. Similarly for the other two. Now, what's the interpretation of this? The interpretation of this is that the following. The probability of more than one events in a small time interval t2 t plus h is almost 0. That's the last fact. That is, probability that nt plus h minus nt greater than or equal to 2 is little o of h. That means it goes to 0 in particular. Of course, this says more than that. It says that this divided by h goes to 0. That means this goes to 0, not only goes to 0, it goes to 0 at a rate faster than h, but nevertheless it's almost 0, and as I said, equals little o of h to be precise. So that's as far as the probability of having two or more events is concerned. The probability of a single event, so that's a middle condition, middle equation. The probability of a single event in a small time interval t2 t plus h is roughly proportional to the length h of the interval. So remember that probability that nt plus h minus nt is 1 is lambda h, so it's a quantity that is proportional to the length h of the interval plus an error, and that error goes to 0 at a rate faster than h. Moreover, this constant of proportionality, that is the probability is proportional to h, that constant of proportionality is lambda, which does not depend on t or h. So it's something, it's a constant that doesn't depend on the location of the interval. Remember, the length of the interval h, but the location of the interval is determined by t. So it does not depend on the location t of the interval. And of course, the probability of no events in a small time interval t to t plus h is roughly 1 minus the probability of a single event, because probability of more than one event is almost 0. Okay, so this is one way to understand these observations. What we now show is much more important. What we show is that, so starting from the definition of Poisson process that we have given earlier, we have derived those facts. But what we want to show is that these properties, along with the independence of increments, actually characterize a Poisson process with intensity lambda. So that is going to be an alternative definition of a Poisson process with rate lambda. So here's the definition, a third definition, so to speak. So a counting process nt with n0 equal to 0 and having independent increments. So these are already part of the hypothesis. So such a process is a Poisson process with intensity lambda if it satisfies for all t greater than or equal to 0 as h goes to 0 plus. You have these three things. So we have seen that if nt is a Poisson process according to a first definition, then these are true, these are correct. But what this says is that, on the other hand, if you have a counting process which starts at 0 and has independent increments and in addition satisfies these properties, then it better be Poisson process with intensity lambda. So that's what it says. So in other words, this gives you a third definition of Poisson process lambda. Okay, so here's a proof. Since n0 is given to be 0 and independence of increments are also assumed, so therefore the only thing to show that nt is indeed a Poisson process according to first definition, we only need to show that the increment nt minus ns for any s less than t is indeed a Poisson distributed random variable, a Poisson with parameter lambda into t minus s. So that was, remember, the condition C in the definition, our original definition of Poisson process. The other two conditions, that n0 equal to 0 and the increments are independent, is already assumed in this. Okay, so showing that nt minus ns is Poisson with parameter lambda t minus s for any s less than t is equivalent to showing that if you take any s greater than or equal to 0, any t positive, then n s plus t minus ns equals Poisson lambda t. So these two are equivalent statements. Okay. So how do I proceed to show this? Well, first let's define Pnt for t greater than or equal to 0. Pnt is the probability that nt equal to n. for n greater than or equal to 0 integer and any t greater than or equal to 0. So for every n, this is a function of t, non-negative t. So what we will first show is that for every n, Pnt is continuous in t. That was the first step. Then we show that it is indeed even differentiable in t on the open interval 0 to infinity. And then as we actually show that it's differentiable, we actually end up showing that it satisfies a simple differential equation that admits explicit solution. And all of this would be done using those conditions that are given in this third definition. Okay, so we continue with this. First, the proof of continuity. So from the hypothesis, what we have is for any t greater than or equal to 0, P0 probability that of t plus h minus P0 of t. Remember, the P0 of t plus h is probability that nt plus h is 0. So what we are saying is that that is equal to the probability that nt is 0 and multiplied by 1 minus lambda h plus 0, little o of h, as h goes to 0 plus. So why is that so? That is so because P0 of t plus h is the probability that nt plus h is 0. Now if nt plus h is 0, then nt has to be 0. So we can write it as this probability as the probability that nt plus h is 0 and nt is 0, which is same as the probability that nt is 0 and nt plus h minus nt is also 0. Now these two are independent increments, so this becomes a product of probability that nt is 0 times the probability that nt plus h minus nt is 0. Now Pnt is the first, P0t is the first factor, the probability that nt equal to 0. And remember, the condition given to us in the hypothesis or in the definition is that probability that nt plus h minus nt is 0 is 1 minus lambda h plus little o of h as h goes to 0 plus. Okay, so it actually comes from the the condition in the definition that we have just given. So from this one can easily deduce. So this is for h positive, but you can also write something similar for h negative. You can easily deduce that if s is not equal to t, then P0t minus P0s is less than or equal to lambda into mod t minus s plus little o of mod t minus s as t minus s mod goes to 0, of course goes 0 plus. T minus s is always positive, in modulus is always positive. Now using the same ideas, one can show that, so this first thing would show that P0 is continuous. But now for general n, for n greater than or equal to 1, one can again show by using same ideas that for s not equal to t, Pnt minus Pns in modulus is bounded up by 2 times lambda times mod t minus s plus little o of mod t minus s as mod t minus s goes to 0. So that clearly shows that as t minus s goes to 0, Pnt minus Pns in modulus also goes to 0, thereby establishing the continuity of P0t and every other Pnt in t, continuity in t. Now we move on to proving differentiability. Note that for any t positive and small h positive, again we can write P0 of t plus h as P0t into 1 minus lambda h per little of h. So this is something we have already seen before. And P0t, if I want to write P0t in terms of P0t minus h, then you can easily see that P0t equals P0t minus h into 1 minus lambda h plus little o of h. That is because if you look at the right hand side, that's the probability that nt minus h equal to 0, and the second factor is the probability that nt plus h minus nt, or rather nt minus h is 0. So therefore you have this. So from this you easily obtain that if you look at P0 of t plus h minus P0t divided by h, then when h is positive, this ratio becomes minus lambda into P0t plus little o of h by h, and when h is negative, use the second equality for the case when h is negative to see that the ratio is equal to, for h negative, minus lambda p naught at t plus h plus little o of h, little o of mod h divided by mod h. So now from this you can easily take the limit as h goes to 0 and show two things. One, P0t is differentiable at t because the limit of the left hand side quotient, there would be limit, and the limit actually, if you compute the limit, it turns out to be exactly minus lambda p naught t. That's clear from the previous equation. Whether you are in the case H positive or in the case H negative, in both cases, limit of this quotient as H goes to 0 is indeed minus lambda into P0t. So that shows that P0 is differentiable and that P0 satisfies this very simple differential equation, namely P0 prime t is minus lambda P0t. Now we want a solution of this equation. This is an easy differential equation, one of the simplest, but then we know that to find the solution of this differential equation uniquely, we also need a boundary condition or initial condition, and that comes from the hypothesis that n0 is identically 0, which would in turn mean that P0 of 0 is 1. So that's the initial condition for the function P0t. So using that initial condition and this differential equation, you can see that you get the solution, unique solution, to be P0t equals exponential minus lambda t for all t greater than or equal to 0. So we have evaluated P0t completely. See, there's no distributional assumptions, but we have obtained it from just the conditions that are given to us. Similarly, now I'm going to look at Pn for n greater than or equal to 1. So let's start with P1 n equal to 1 first, just as a startup. So if you fix any t positive and small enough h positive, then again, exactly as we have argued before, P1 of t plus h, which is the probability that nt plus h is 1. Now that can happen in two possible ways. One is probability that nt is already 1 and nt plus h minus nt is 0, or probability that nt is 0 and nt plus h minus nt is 1. So either that event has already occurred before time h, before time t, and between time t and t plus h there are no events, or no events took place up to time t and there has been one event during the interval t to t plus h. Of course, other possibilities are ruled out, because if the interval is small, and in fact we are going to take the limit as h goes to 0 plus, we know that the probability of there being two or more arrivals in that small interval, that probability is almost 0, negligible. Okay, so this is what you have from those considerations. And similarly, P1t would be equal to P1 of t minus h times 1 minus lambda h plus little o of h, plus this P0 of t minus h into lambda h plus little o of h. I mean, you just get this by simply, for the t minus h equality, what you do is you try to look at the probability, the left hand side, the probability that nt is 1. Again, argue that can happen only two possible ways, the other being probability being 0, namely that either one event has already occurred up to time t minus h and no events during the time interval t minus h to t, or no events have taken place up to time t minus h and exactly one event have taken place in the interval t to t plus h, t minus h to t. So you get this. So as a result, if you now simplify, do some algebra and try to write down this quotient P1 of t plus h minus P1 of t divided by h, then one can easily check that this is what you get to. So for h positive, you get lambda into P0t minus P1t time plus another error term, which is like little o of h by h, and since it's little o of h by h goes to 0, and similarly you have another one for h negative. The point is that now if you let h go to 0, you will see that both formula that is, if you let h go to 0 plus, then you have to look for the limit of the first expression on the right hand side, and if h goes to 0 minus, then you have to find the limit of the second expression on the right hand side. But if you actually do that, you can easily verify that you end up getting the same limits, which really means that P1 is differentiable, and not only that, it satisfies this, again, a very simple differential equation. Now, again we'll use the hypothesis that n0 equal to 0, that is P10 is 0, Remember P00 was 1, whereas P10 is 0. And use that to get the following solutions. That P1t is lambda t into exponential of minus lambda t. This is true for every t greater than or equal to 0. So having done it for n equal to 0 and n equal to 1, let's now go to general n. So here is one simple fact from ordinary differential equation theory that we are going to recall. If you have a function f which satisfies this differential equation f dash plus alpha into f equal to g, suppose that has a unique, so this differential equation actually has a unique solution, and that unique solution is given by ft equal to exponential minus alpha t times that square bracketed quantity. Now this easily obtains by multiplying both sides of the original differential equation by e to the power alpha t, and then quickly seeing that if you do that, then the left hand side becomes just the derivative of the product e to the alpha t into f. So it's the left hand side is just the derivative of that, and from there you can find out this solution. Okay, so now let n greater than or equal to 2. I want to do the same thing for n greater than or equal to 2. So once again, for t positive and small enough h positive, I'll write down an expression for pnt plus h, which is equal to this, and that implies that the right hand side derivative of Pn at t turns out to be lambda into Pn minus 1t minus Pnt. Similarly, one can see that if you take any t positive and small enough h positive, then P tilde Pnt is Pnt minus h by the same argument plus lambda h into Pn minus 1t minus h minus Pnt minus h and little of h. Okay, so this implies that the left derivative turns out to be the same as the right derivative. So now again use the fact that n0 is 0. See, P00 was 1, but for n greater than or equal to 1, Pn0 is 0, because the probability that nt is positive, n0 is positive, that is 0. So once again using that, you look at this differential equation, and that turns out that has a unique solution given by Pnt is lambda into exponential of minus lambda t times the integral 0 to t Pn minus 1s ds. Now notice that we have already obtained P0t as exponential of minus lambda t. We also obtained P1t as lambda t into exponential of minus lambda t, and then the differential equation is an equation that connects the derivative of Pn, the function Pn, and also the function Pn minus 1. So one can do this by induction. So if you let n greater than or equal to 2, once again for small h etc., you have Pnt plus h is written like this. So you have the first derivative, and then you have the second derivative. Both the left derivative and the right derivative, and both the left and the right derivative turn out to be the same. So therefore what we get is that Pnt for every n satisfies this differential equation, Pn prime t plus lambda Pnt equal to lambda Pn minus 1t. Now use that formula for general solution of an equation f prime plus alpha f equal to g. We have exactly something like that. So therefore using that, you can easily see that this differential equation for mu n has a unique solution for mu n, which is given by mu nt is, or rather Pnt is lambda into exponential minus lambda t integral 0 to t Pn minus 1s ds. Okay. But now we have already proved that P0t is exponential minus lambda t. P1t is lambda t exponential minus lambda t for all t greater than or equal to 0. So one can now use induction. Suppose you have obtained all the way up to Pn minus 1t, then plug that in that equation above in the second term of the right hand side, then you can actually use that and find the solution to be given by Pnt equal to this formula. And what that means simply is that remember this turns out to be the probability mass function for a Poisson random variable with parameter lambda t. So we get the result that we wanted, namely Nt is a Poisson random variable with parameter lambda t. Okay. Now to complete the proof, so what we have shown is only about P and T. That it doesn't complete the proof. So it shows that Nt is Poisson, because P and T is the probability that Nt equal to k. So that shows that Nt is Poisson, but that's not enough. We have to show that every increment is Poisson with the parameter lambda times the length of the interval. So towards that, it's very easy now. So what you do is you fix S positive, non-negative, and define P tilde Nt to be the probability that Ns plus T minus Ns is N. So we want to show that this is also Poisson with parameter lambda into T. Now, if you look at the increment of this new process, namely the process n t plus h minus ns plus t minus ns, say for this new process, the increment between ns plus t plus h minus ns and simply ns plus t minus ns is nothing but the increment of the original n over the interval s plus t to s plus t plus h. So therefore we can apply the same conditions, which means that the PNTs that we defined here, or Pn tilde t rather, they also satisfy this exactly same continuity differentiability holes, and not only that, they satisfy the same differential equations. And initial condition, of course, is that P00 is 0, or P00 is 1 rather. So one can therefore conclude that P tilde Nt is lambda t to the power n over n factorial times exponential of minus lambda t for all n greater than or equal to 0, which means that Nt plus s minus ns is indeed Poisson with parameter lambda t. Okay, so here are some remarks. The reason why the parameter lambda is called the rate or intensity can be interpreted in two different ways. One is a very simple-minded way of interpreting it, namely that lambda gives you the expected value of the number of arrivals for a pp lambda. That's immediate from the definition. And the fact that Poisson random variable with parameter, let's say alpha, has expected value alpha. But there is a second and sort of more intrinsic way of thinking of this lambda. Why is it called? Why is the process called a Poisson process? So that is that reason comes from the definition of pp that we have given. It says that for a small time interval t to t plus h, we can ignore the possibility of more than one arrivals, and then the probability of an arrival during the small interval is lambda times the length of the interval. The third definition of pp lambda as a counting process with independent increments and satisfying certain conditions on the probabilities of arrival in small time intervals leads to a natural generalization known as the non-homogeneous Poisson process, where the rate or intensity is allowed to vary with time. So let's see what we mean. So here's a definition of what is called a non-homogeneous Poisson process. So for this, what we want is, we don't want a single constant lambda positive, but we want a function lambda on the positive real lines into positive real lines, which is locally integrable. By that I mean that if you take any finite interval in the domain of definition of this function lambda. So that means it's so for all positive lambda, and so this is locally integrable. And locally integrable means that if you take any finite subinterval of 0 to infinity, then on that finite subinterval, on every such finite interval, x has a finite integral. So that's what is often meant by saying locally integrable. Okay, a counting process NT with independent increments, that's assumed, and with n0 equal to 0, that's also assumed. So what is new? So such a process is called a non-homogeneous Poisson process with intensity or rate function lambda if for every t greater than or equal to 0 and h going to 0 plus, we have these three quantities. So what we have seen is that that you already have the distributional property satisfied, provided you assume these conditions. Of course, pp lambda is a special case when the intensity function lambda is a constant. That is, lambda t is equal to lambda for some constant positive lambda. This is why sometimes a pp lambda is called a homogeneous Poisson process. Okay, so we continue with non-homogeneous Poisson process. For a non-homogeneous Poisson process, the increments still remain Poisson random variables, just like in the homogeneous case. But what is lost is the stationarity may be lost. So to see this, let's fix any s greater than or equal to 0, and as before define Pnt to be the probability that n s plus t minus ns equal to n. So I am looking at the increment over the time interval s to s plus t and looking at the probability that that increment takes the value n and calling it Pnt. We want to show that this is the probability mass function of an appropriate Poisson distribution. In our definition of non-homogeneous Poisson process, there was no distributional assumption. It was only those infinitesimal conditions. Now, through similar analysis as was done in case of homogeneous Poisson process, one can show that this Pnt n greater than or equal to 0 satisfy following differential equations. Namely, P0 prime t is lambda t into P0 t. So the difference this time with the homogeneous case is that there we had a fixed lambda, but now we have lambda t. And the other thing is that for any n greater than or equal to 1, the differential equation solved by or satisfied by Pn is Pn prime t plus lambda t Pnt equals lambda t into Pn minus 1t for n greater than or equal to 1. Now again, one has the same initial conditions as in the homogeneous case. The initial conditions do not change because n0 is assumed to be 0, which means P0 0 is 1, Pn 0 is 0, or Pn 0 is 0. For all n greater than or equal to 1, because at time 0 there are no events. So using this, one can then get the unique solution of these differential equations exactly as before, turn out to be Pnt equal to exponential of this quantity, this integral s to s plus t lambda u du, and then a ratio, this integral 0 to s plus t or rather s to s plus t lambda u du mu to the power n divided by n factorial. This is true for every n greater than or equal to 0. And what does it mean? This is clearly the probability mass function of a Poisson distribution, and you can also identify the parameter. So this implies that s plus t minus ns is a Poisson random variable, and the parameter of the Poisson random variable is the integral s to s plus t of lambda u du. So you take the intensity function, integrate it over s to s plus t, that gives you the parameter of the Poisson process or the Poisson random variable, which represents the distribution of number of arrivals in any fixed time interval nt plus s minus nt. Okay. Thus, when the increments of a non-homogeneous Poisson process are all Poisson random variables, but the increments may not be stationary. Okay, because if you go back to, so it's a Poisson with parameter is integral s to s plus t lambda u du, and that won't be the same as the integral of 0 to t lambda u du, which would be needed for stationarity of the increments. Okay. In fact, stationarity of the increments, that is nt plus s minus ns is the same as nt in distribution for all s greater than or equal to 0, t greater than 0, would clearly imply that the integral, so if you compare the parameters of nt plus s minus ns and the parameter of nt, then equality must hold for integral 0 to t lambda u du and integral s to s plus t lambda u du, and then by a change of variable the second integral can be converted into integral from 0 to infinity. The integrand becomes lambda u plus s du, and this should be true for all s greater than or equal to 0, all t greater than 0. Of course, if you compare the first integral with the last integral, it says that you have two different functions. One is lambda u, the other is lambda u plus s, function of u, and its integral from 0 to t agree. The integrals of these two functions from 0 to t agree for every t. So the two functions must agree, of course, almost everywhere. So the conclusion is that if that is so, that is, if you have stationarity, then it would follow that lambda must be almost surely a constant. Thus, we have stationarity of increments if and only if the Poisson process is homogeneous. Now, just as in the case of pp lambda, one can show that NHPP has the following alternative definition, which is equivalent to the definition that we have just given, namely that a counting process is called a non-homogeneous Poisson process with rate or intensity function lambda if n0 is 0, and then there is condition on independence of increments. So this is exactly the same condition that appears in the definition, first definition of homogeneous Poisson process. And last condition that we have is that for s less than t, the increment nt minus ns is Poisson, but the parameter is the integral s to t of lambda u du. And the major difference is here. In case of homogeneous, we had this is Poisson with parameters lambda into t minus s, where lambda is a fixed constant, by which it meant that the distribution of nt minus ns is same as that of nt minus s. But here, of course, we don't have that. So that's basically something that one can show by following the same arguments that was used for showing that the first definition of Poisson process, homogeneous Poisson process, and the third definition involving probabilities of events 0 or 1 or more than 1 events in a small interval. So there was a definition so that these two definitions for homogeneous Poisson process were shown to be equivalent. Now in fact there is no different argument that is needed to show that for non-homogeneous case also this provides another equivalent definition. 40. So as we said in the beginning, that the major thrust of this module was to get this third alternative definition of Poisson processes by this so-called infinitesimal properties. Namely, in addition to starting from 0 and having independent increments, we showed that if the counting process is assumed to have these three properties, that in any small time interval, the probability of there being two or more intervals goes to 0 at a rate faster than the length of the interval. The probability of there being exactly one arrival is proportional to the length of the time interval plus an error which goes to 0 at a rate faster than the length of the time interval. And of course, probability of there being no arrival in that small time interval is 1 minus these two. So if a counting process, apart from independent increments and starting from 0, has these properties, then it automatically becomes a Poisson process, and the rate becomes that constant of proportionality that we got in the context of probability of there being one arrival during a small time interval. But we didn't stop there. This gives us a very intrinsic interpretation of why the quantity lambda is called the rate or intensity of the Poisson process. Secondly, we move forward. This also led to a natural extension or generalization of this concept, where the rate may not be kept constant, but instead the rate may be allowed to depend on vary with t, which led to a new notion of what is called a non-homogeneous Poisson process. And then we showed that a non-homogeneous Poisson process can also be defined via starting from 0, having independent increments, but having and increments having a Poisson distribution, except that it may not be stationary anymore, unlike the homogeneous Poisson process.